So what I want to say is that we find like before that theoretically we have trace of IB of W equals 0 separates the separable state from the integral state. Like if it is strictly infinite to 0, you're into integral states, and so that's alright. But there is a fundamental problem with this is that characterized mathematically the ensemble of separable states is NP-hard. Um, Trying to ask a computer to find W that never gets the block of separable states is a really impossible calculation to do in practice. So one solution can be like to create a PPT to do a relaxation with the PPT sets that englobe the separable states, because the positive partial transpose will let us define a constraints semi-positive definite and do after semi-positive optimization about it. So we have AB uh, with a trace over A that is semi-positive, and so it will be really easy for a computer, as we see, because we have method for semi-definite programming. Yeah. To exploit this relaxation, we just need to put an optimization problem that searches the minimal value of lambda of the transpose matrix. And if lambda will be strictly infer to 0, we'll know it will be entangled. So basically, this problem is just, if you write it, it's just a problem. I just say like max of lambda such that rho AB Ta minus lambda I is semi-positive definite. And so the principal idea there is that calculate lambda is easy, but it does not give us our physical object to measure, and that's why we need to go to the dual. And thanks to strong duality, the dual will just give us the optimal W that relies the minimum, and we obtain then our minimum such that trace of rho AB of W equal lambda, which is inferior to lambda itself. No, so basically, if you do like the stuff, we know just for primal just like this. And so we just have to calculate the Lagrangian about it, so lambda stays the same. We just create W to our matrix, and so we just have lambda plus the trace of W multiplies by rho AB Ta minus lambda E, and where we introduce W, and so maximizing over the Lagrangian over lambda, we arrive at the dual SDP, which says like minus of W of the trace of W multiplied by BTA, such that the trace of W equal to 1, and W is semi-positive definite. Yeah. So that's it. So we just have this, and so we just get that with the change of variables, we just get well, that we're going to reach Ta. We just have minus W of the trace of WAB or AB such that the trace of W equal 1 and WTA is semi-positive, and as those two problems are strongly dual, which means that for some given state ray B, if you compute T star of ray B and find it strictly smaller than 0, then the ray B is not into PPT, and hence ray B is entangled. So far nothing too impressive has happened. Largely we have managed to overcomplicate the computation of the minimum negative value, but the important observation for application comes by looking at the feasible point of the double problem. Given any feasible W, we have by weak duality that trace of ray BW is superior to T of ray B, which is superior to primol of ray B, and so the trace of ray B W inferior to 0 implies that ray B is entangled. This means we can potentially use the witness for many different states, and geometrically we solve the dual SDP for given state ray B and extract W and then this witness in some sense optimal for the state. It will also work for other entangled states, but not necessary for all entangled states. So yeah, basically what I wanted to say is like we obtained if lambda is inferior to 0, we know it's entangled, thanks to strong duality, which will give us the optimal W, and the major interest of this method of this dual method resides in the fact that the contrasts on the matrix W in the dual problem, do not absolutely depend on the state ray B that we test, which signifies that once the computer has generated the W testimony from our state, we can recirculate it, and we can take it into the laboratory and use it for testing an affinity of other states by simply making a measure about trace of throw new W, and if it is negative, then the the testimony of it proves that entanglement prevents the entanglement instantaneously without having the need to relaunch the optimization. So to conclude, and to synthesize, we just showed that we need PPT because separate knowing if it is entangled or not, the separative problem is NP hard. Thanks to our dual problem on ISTP optimization, thanks to the constraints of PPT, which is semi-positive definite, we can link the eigenvalues calculation to W, thanks to duality, and use and have a usefulness in practice to find this W that can be measurable and reusable.